task for this week is to have a quick view towards what we call ordinary differential equations. So usually the people write them as ODEs, if it's in plural, ordinary differential equations. So why ordinary? Ordinary means that you have got just one variable there, and that will have big impact. We shall come that to back in next semester. But for now, let's just review again what we've been doing with the integration from this perspective. So if we write in differentials what we've been doing in the Newton approach, it was the following. So we had the dy, and this equals f x dx. That was the relation of two differentials, right? So of course, why couldn't this be of more general form? Why couldn't we have something like, say, g depending on both of the variables times dy equals f depending on both of the variables times dx? That's just a combination of two linear forms which is dependent. So the coefficients here are dependent on both variables, the values of x, the independent one, the value of y, the dependent one. But more generally, who cares which one is which? I simply have two concepts, two objects called x and y, and I know that the linear approximation between them is given in such a way. So actually, usually we do not have this, right? So this is there only to catch things where you can't differentiate. So if it was zero, right? But that's sort of strange. So let's avoid this. So we would have just this nice equation. But this is too complicated to solve now. We come back to that in the future. But for now, let's come back to this simplest situation which we already dealt with. That's actually finding the antiderivative. So we solve a equation y dash equals f of x, right? And we know that the solution is the primitive function, so the antiderivative. So we know that y of x equals, as you can read on the right hand side, integral from a to x of some f t dt, plus there is the freedom in choosing the constant. And this can be fixed by taking fyx equals say some y0, and that will be plus integral, and I would say right here t0x ft dt. And now you see that the constant, this one, has been chosen in such a way that the value of y at the point t0 is exactly y0, right? Because if x is t0, the integral doesn't contribute anything, and so the quantity y dependent on the quantity x is just described explicitly this way. Right, if not explicitly in terms of analytic formula, then at least numerically we can solve this. We shall come to that soon. But of course, the most general case is too difficult for us now, but let us focus on the special one, where on the right hand side we have a formula which is called a formula which is separated in variables. So that's this separated variables name. And then of course what we can do is something which is close to what I was starting with. So supposing that the g at some given y is non-zero, then we can divide by that. And in terms of differentials, so how I had it here or here, that's the right thing. So I can simply move the g to the left hand side and I get this. And now what does it mean? So I have got some prescription on the left hand side which will have some primitive function, and some prescription on the right hand side, which will have a primitive function 2, both under the assumption that the functions g and f are nice enough, right? And then it means that you can simply write them in an equality. So if capital G was the primitive function to, so well, that's not the right thing. If G dash would be in y would be 1 over gy, and f dash in x would be fx dx, well, no, just fx, then as it's easily checked, we have an equation gy equals fx, and that's a sort of description of our solution. So why sort of? Well, because we would like to see the solution in a form y equals something in x or x equals something in y. And this is what the people call implicit function formula, right? And in practical situations, simply we write this and we try to compute y as a function depending on x, and usually it's possible. So just to have a look at some example. So the simplest example is this one. So it's just the opposite of the antiderivative in the Newton integral style. So here we have got a equation where the x doesn't appear at all on the right hand side. So it's a special case of the separated variable equation, and you see you simply divide by y and you get on the left hand side the primitive function ln y in absolute value. On the right hand side you get x plus c, and so after some thinking you get that yx equals d times the exponential function, and all possibilities for a constant d work. So the negative ones will give us the negative values of y, the positive ones the positive, while d equals 0 will be the constant solution for the 0, right? So that's exactly what we would aim at. And then one more comment. So as I told, it's just a glimpse towards ODE, so I will not go into details here, but what about analytic solutions? So of course, if we deal with the integration task, which is considered to be a special case of ODEs, the separated variables, then of course we know that the power series, so if f is analytic, that means f is given by a power series, this one. And of course we know the power series are integrated and differentiated term by term. So we know exactly what the solution will be, right? That's this. Very easy going. Actually, it's a mistake here. It should be n goes from 1 to infinity. 1 to infinity, not 0. Because the y0 is just what comes here at the 0 power of x, right? At 0. Right, but what about if we have the other extreme? I mean, again, in 1 year, in the other course, well, actually not, in the next semester. In the next semester, in the extension of our analysis course, we shall deal with the ODEs, and we shall learn about the Cauchy-Kovalevska theorem, saying that if the right-hand side is analytic, then the solution is analytic. But here you might have a glimpse how it works in the very easy situation where the right-hand side is depending just only on y. And then first of all, you can see that it's easy to understand that by the very equation you can compute all the further derivatives, right? Because you simply know that f is analytic, so you can differentiate and you get simply inductively you get all the derivatives. So that's easy, but the problem is whether the formal power series written with those derivatives will be converging to the solution. And some quite smart trick, which is called the measurand approach, based on the observation that if you understand this iterative inductive procedure in computing the derivatives, then for all of them you can prove inductively that there will be a formula given by a quite complicated and not necessarily easily computable polynomial Pn in general, but it's a universal polynomial which is always the same one for all the equations, and all the coefficients of the polynomial are always positive, and that will be a crucial thing in the proof of this nice Cauchy-Kovalevskaya theorem in dimension 1. And the theorem says that simply the derivatives which you compute give you a power series which really computes the solution. So that's very nice and very straightforward. So even in some situation numerically could be of interest. And here you see it's no way very complicated. Right. So I think that's for this very presentation, and have a nice day.